Hello, good evening.
Good evening, sir.
Good evening, sir.
Any doubt from last class to any one of you? Okay, so we have started isobaric process, which is also called Charles law. So at constant pressure, volume and temperature should be directly proportional to each other. And molar specific heat for constant pressure will be Cp, which may be calculated using this expression in terms of gamma or in terms of degree of freedom like this. Now we have to plot curve related to different thermodynamical variable for this process. So we mainly have 6 different types of graph, 3 for expansion and 3 for contraction. All graphs which define state or condition of gas is also called indicator curve or indicator diagram. Indicator graph. First for pressure versus volume. Pressure versus temperature. Volume versus temperature. So in first part, pressure versus volume, pressure versus temperature, and pressure versus volume versus temperature. First, since pressure is constant, so graph for this pressure versus volume curve will be straight line from this point to this along this way. Similarly, in second part, since pressure is constant, so again, it will be along this way. For third part, since volume and temperature is directly proportional to each other, so graph will be a straight line like this. Gautam, is it clear?
Yes, sir.
Now for third part, we have to define some quantity related to this curve. We may write ideal gas equation as PV is equals to nRT. Since in this curve we have volume in numerator, that is in along y-axis, and temperature is denominator, that is along x-axis. So move this temperature to left side and pressure to right side. So you may write volume divided by temperature equals to nR divided by P. This quantity will be perpendicular by base. So it tells you about this particular curve, nothing but slope. N, number of moles, R, universal gas constant. So these two terms is constant. So we're left with just pressure. So this slope will inversely proportional to pressure. So greater the slope of volume versus temperature curve, it will have smaller pressure. Nabila, is it clear?
Yes, sir.
Just write it down to this.
Done, sir.
So slope is more for the blue line, right?
Slope is
More for the blue line, right?
I'm unable to hear you, Gautam.
The blue line has more slope, right?
Yeah,
Steeper.
it having more inclination, it having lesser inclination. So greater the slope, it will have smaller pressure. So let's say this is A and this is B. So in this case, you will say A having more slope, so it will have lesser pressure as compared to B. You all have written? Raza, done?
Yes, sir. Done.
Okay. Now, related to this PV curve, we have to first calculate slope of pressure versus volume graph. Since this line is parallel to x-axis, so its inclination with respect to x-axis will be 0. So slope dp by dv, that is tan theta, will be 0 in this case. Now, related to this slope, you'll have to calculate bulk modulus, which I have defined this in mechanical properties of solid. Beta equals to dp by dv with negative sign multiplied by volume. In solid, I define you beta equals to volumetric stress divided by volumetric strain. Volumetric stress is perpendicular force acting on a particular area. Perpendicular force by area is also called pressure. So you may call it as change in pressure divided by volumetric strain, delta V by V with some negative sign. This particular quantity for instantaneous may be written as dP by dV, and this volume get multiplied with some negative sign. So in general, beta will be minus of dP by dV times V. Gautam, is it clear?
Yes, sir.
Next is, since dP by dV in this expression is 0, so beta will be 0. It means this system will not have any elasticity. Next, work done. Work done will be equals to area under pressure volume graph. Since this particular graph is going from some initial volume to final volume, keeping pressure constant, so it will be area under pressure volume graph. So it will be P constant, V final minus V initial, which may be written as PV is equals to nRT. So it will be nR temperature final minus temperature initial. So either using pressure versus volume or using for temperature, you may find work done related to this process. Nabila, any doubt?
No, sir.
Next question will be heat supplied Since dq equals to nc dt, where C is also called molar specific heat at that process. So in this, we are using isobaric. So C will be Cp. So it will be also equals to N times gamma R divided by gamma minus 1 into dt. So on equating dq work done, let me define you a generalized relation to find dq equals to gamma times du, which is also equals to gamma divided by gamma minus 1 work done. I'll define you this particular formula from where I have derived in next process. Okay. Any doubt related to this part to any one of you?
Sir, how did you get RDU?
Which part?
Sir, how did you get RDU?
RBU.
RDU. DQ is equal to RDU.
This is gamma.
Okay, gamma DU.
Gamma du. Okay, okay. In above part, in concept of internal energy, I defined you du is equals to number of moles R dt by gamma minus 1. In this part, we have dq equals to n times gamma R dt divided by gamma minus 1. So just divide these two parts. Gamma minus 1 will cancel out, and R dt will cancel out. So you're left with du by dq equals to 1 by gamma. That's why dq is equals to gamma times du. Is it clear?
Yes, sir. Yes, sir.
And then on putting all the values and first law, I have just derived the third part, which is equals to gamma times work done by gamma minus 1. Yusra, any doubt?
No, sir. Done, sir.
Nabila, done?
Yes, sir.
So gamma dw by gamma minus 1, that we will define later, right? The derivation.
You may use first law, put the value of dq and du, you'll get this part.
Okay,
Okay.
sir.
Should I derive?
So yes,
Okay.
please. Yes, if you can.
Just 1 minute. Using first law, we may write dq equals to du plus dw. Since I have to calculate dq and dw, so just write du in terms of dq. So it will be 1 by gamma times dq plus dw equals to dq. Move this dq to left side. Equals to dw. Take dq common. Then on taking LCM, you're left with this part. Now move all the quantity to right side. So dq will be equals to gamma divided by gamma minus 1 times dw. So I have dq is equals to this, and from this part, dq equals to gamma times du. So we have same quantity in left side for both these two terms. So in general, I can say dq equals to gamma times du, which is also equals to gamma by gamma minus 1 times dw. Gautam, is it clear now?
Yes, sir.
Okay.
Done, sir.
Minashi, done?
Yes, sir.
Let's say this is pressure versus volume graph. Point A, point B. Twenty centimeter cube, 50 centimeter cube, 2 atm pressure. If temperature at A is 27 degrees Celsius, find first temperature at point B, second work done, third heat if gas is helium. Let me give you a hint how to approach this part. First, we have temperature at A. So convert it in terms of Kelvin. So you can write temperature at point A will be 273 plus 27, that is 300 Kelvin. We have to calculate temperature at point B. Now this is isobaric process for which equation of state is V1 divided by T1 equals to V2 divided by T2, or you may write VA divided by TA equals to VB divided by TB. So putting all the values, you may find T2 or temperature at point B. Nabila, is it clear?
Yes, sir.
Next, you have to calculate work done. Work done is nothing but area under the graph. So just try to calculate area of this particular curve. In this, 1 centimeter cube will be 10 to the power minus 6 meter cube, and 1 atm will be 10 to the power 5 Pascal. Try to solve using these given terms. Good, Gautam. Try to solve third part. Good, Krishna. Good, Minashi. Yusra, you got any answer? Nabila?
2 minutes, sir.
Okay. Good, Raza. Yes, Yusra, do you want to ask something? Good, Raza. Let me solve first part. We have volume V1, 20 centimeter cube, 10 to the power minus 6. T1, temperature at point A, 300 Kelvin. V2 is 50, 10 to the power minus 6. Temperature at point B, we have to calculate. So just rearrange it. TB equals to 15 to 10 to the power minus 6. Third 300 on moving to right side, it will get multiplied to it. Whole divide by 20 into 10 to the power minus 6. So on solving, you'll get 750 Kelvin. Nabila, you got the same answer?
No, sir, I did a mistake in calculation.
Okay. Next, for work done, which is nothing but area under this graph. So work equals to pressure times V final minus V initial. Nabila, just tell me the value of pressure for this system.
2 into 10 to the power 5.
Good. Initial volume, final volume.
Initial is 20 and final is 50.
So 50 minus 20 into 10 raised to minus 6. So 2 into 50 minus 20, 30. 10 to the power plus 5 and 10 to the power minus 6. It will be 10 to the power minus 1. So 20 into 2 into 30, 60 into 10 to the power minus 1. That will be just 6, 2. Now, we have to calculate how much heat is being supplied to the system for this particular process. So we have given helium gas. Whether helium is monoatomic, diatomic, or triatomic. Gautam?
It's a diameter, monatomic helium.
Good. So what will be the value of degree of freedom for monoatomic gas?
3.
Good. So gamma will be
1.67.
in terms of fraction.
5/3.
Good. So we had a relation dq equals to gamma divided by gamma minus 1 times dw. Put the value of work done and gamma and simplify it to find heat. Okay. Raza, just check your calculation. Minashi, just check your calculation. Good, Krishna. Let me solve. We have gamma equals to 5 by 3 whole divided by 5 by 3 minus 1 multiplied by work done, that is 6. So in numerator, we have 5 divided by 3 whole divided by, in denominator it is 5 by 3 minus 1. So on taking LCM to be 3, 5 minus 3 will be 2, divide by 3, good Nabila, into 6. This 3 and this 3 will cancel out. So you're left with 5 by 2 into 6, that will be 15 joule. Gautam, is it clear?
Yes, sir.
You all have done to this part?
Yes, sir.
Okay. Next is isochoric, which is also called isometric. Gay-Lussac's law, it states the process which is carried out at constant volume is called isochoric or isometric process. The process which is carried out at constant volume is called isochoric process. So according to ideal gas equation, PV is equals to N into R into T. If volume is constant, so pressure and temperature will be directly proportional to each other. So volume is constant or change in volume is 0. So pressure is directly proportional to temperature. So P1 divided by T1 must equals to P2 divided by T2. So this will be equation of state for this process. Now, according to generalized equation, P to the power 1 by x, B equals to constant. So if we have to somehow make this volume to be constant, so P will have to neglect. So the value of x for which this P will get vanished out will be infinity, since 1 over infinity will be 0, and any number to the power 0 will be 1. So it will get vanished. So volume will become constant. So x related to this process will be infinity. Now putting the value of x to be infinity in molar specific heat, you will get molar specific heat at constant volume it will be CV equals to R divided by gamma minus 1 minus R divided by X minus 1. If X is infinity, so infinity minus 1 will be infinity, and 1 by infinity will be 0. So this entire term will get cancelled out. So you're left with just R by gamma minus 1, or in terms of degree of freedom, it will be F by 2 times R. Gautam, is it clear?
Yes, sir. But how is it F by 2 into R?
How is?
How is it F by 2 into R?
In first class, I defined the relation between gamma and F. Gamma is equals to 1 plus 2 by F. So if you move this 1 to left side, so gamma minus 1 will be just 2 divided by F. That's right. Okay.
Okay, sir.
Just write it down.
Sir, can you please explain it once more?
Which
The-
part?
The molar specific heat at constant volume.
In first class of thermodynamics, I defined you a generalized expression. This. In general, equation of state for any particular gas will be PV to the power x or P raised to 1 over x V equals to constant. So you may use the left hand side expression, or you may use the middle one, or this right hand side. This is valid only in case of ideal gas. In general, we can use either this term or this term. So in this part, since I have to make this volume to be constant, so what should be the value of x? So for which this term of pressure will get vanishes. So x will be infinity. So 1 over infinity will become 0. So p to the power 0 will become 1. So you're left with volume equals to constant. That's why x will be infinity in this case. So putting the value of x in this expression for generalized specific heat, which is R by gamma minus 1 minus R by x minus 1. So if you put the value of x to be infinity, so infinity minus 1 will be infinity, and 1 by infinity will be 0. So this entire term will get cancelled out. So you're left with C equals to R by gamma minus 1, which I have done in this part. Okay, Yusra?
Okay, sir. Thank you, sir.
Done, sir.
Nabila, written?
Yes, sir.
Okay. Now we have to plot indicator curve related to this part. Pressure versus volume, volume versus temperature, and pressure versus temperature. In first part, since this process is going at constant volume, so there will be no change in its volume. So it will be straight line parallel to opposite coordinate like this. In second part, since volume is constant, so it will be straight line. For third part, since pressure and temperature is directly proportional, so it will give you straight line. So according to equation, ideal gas equation, we may write PV equals to nRT. Now move T to left side and volume to right side. So P over T will be equals to nR divided by V. So P upon T for this curve will be defined as slope and is inversely proportional to volume. So we can say greater the slope of pressure versus temperature, it will have smaller volume. So let's say there is another curve. If let's say this is B and A, slope of B is greater as compared to A, so it will have smaller volume. So volume of B will be smaller as compared to A. Gautam, is it clear?
Yes, sir.
This is similar to what I have defined above for isobaric process, in which we had curve for V versus T. Raza, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Done, sir.
Next, related to this pressure versus volume curve, we have to define first slope dp by dv. Since this particular line is perpendicular to x-axis, so its inclination will be 90 degree and tan 90 will be infinity. So slope of this graph will be infinite. Now, using this bulk modulus, beta equals to minus of dp by dv multiplied by v. Since dp by dv is infinite, so it is infinite. It means this system will behave as perfectly rigid. That's why bulk modulus is infinite. So it will behaves as perfectly rigid. Next, we have to calculate work done related to this curve.
So can you explain that again, the infinity part?
Bulk modulus, that is beta, which is equals to dp by dv multiplied by v. And since dp by dv, that is slope of this particular curve, is infinite, since this line is inclined normally to this horizontal x-axis, so it will be tan 90 degree, and tan 90 is infinity. So if you put the value of dp by dv to be infinity in this part, you will get beta equals to infinite. Now, this bulk modulus, or simply modulus of elasticity, simply defines you the elastic behavior of that particular substance. It also defines you the more the value of modulus of elasticity, the harder or more difficult it would be to deform its shape. So in this part, since we have beta equals to infinity, so it will be impossible to deform the shape of this particular object. It means it behaves as perfectly rigid body. Is it clear? Gautam?
Yes, sir. Yes, sir.
Okay. Now, work done for this case, since there is no change in volume in this part, so change in volume is 0. So work done in this case will be 0. So the total amount of heat supplied to the system must be utilized only in changing external energy. So using first law, we can say dq equals to du plus dw. Since dw is 0, so du is equals to dq, and dq in this part will be n times c dt, and c in this process will be cv, that is molar specific heat at constant volume, and it will be n times r by gamma minus 1 times dt. Krishna, is it clear?
Yes, sir.
Just write it down.
Done, sir.
So how did you get nr gamma minus 1 dt?
I've just put the value of cv, which I have derived above. Okay.
Oh, okay.
I'm just giving you 5-minute break. I'm returning back. Okay. Okay. Now there will be a question related to this part. I defined you 2 molar specific heat for 2 different processes. One is Cp for isobaric process, and the other is Cv, that is at isochoric process. So first question will be, what will be the relation between Cp and Cv? That relation is also called Meier's relation. So you have to derive Meier's relation. Second, in these two parts, Cp and Cv, Cp will be greater as compared to Cv. So question will be, why Cp is greater than Cv? Okay. So let me define you these questions and how to solve. Suppose in first part, in a vessel, piston is movable. So when you supply heat to this particular system, this heat may get converted in changing internal energy or doing some useful work. But in second part, suppose this piston is locked or fixed. It means there is no possibility of changing volume in this case. So the amount of heat supplied to the system must be utilized only in changing internal energy, and there will be no case of work done in this case. Is it clear?
Yes, sir.
So in first part, at constant pressure, amount of heat supplied must be utilized in changing internal energy as well as doing work. But in second part, at constant volume, amount of heat supplied to the system is utilized only in changing internal energy, since work done in this case at constant volume will be 0. Now, suppose at constant volume, I have supplied 10 joule heat to the system. So how much energy is utilized in changing internal energy for this part? You will say 10 joule, complete part. But if I suppose supply 10 joule at constant pressure, so there will be possibility of 9 joule energy conversion to internal energy and 2 joule in some useful work. Is it clear?
Yes, sir.
Yes, sir.
So if I had to somehow take or calculate, or if I have to get same amount of internal energy for both these two processes, so what will I do? We have to increase the amount of heat supplied to the system. Let's say on increasing this particular quantity to 14 joule, it will become 10 plus 4. So if same amount of internal energy for both these two processes, so we must supply some extra amount of heat in the case of constant pressure as compared to constant volume, since at constant pressure, the amount of heat supplied to the system is utilized in changing internal energy as well as work done. That's why we have to apply some extra amount of work or some extra amount of heat as at constant pressure as compared to constant volume. That's why Cp is always greater as compared to Cv. Gautam, is it clear? Why
Yes, sir.
Cp is great? Yes?
Yeah, we had to supply extra energy to change the internal energy.
Yeah, some extra amount of heat at constant pressure to get same amount of internal energy in both cases. Okay?
Yes, sir.
So in statement, we can say at constant volume, heat supplied to the system is utilized in changing internal energy only, but at constant pressure, heat supplied to the system is utilized in changing internal energy as well as work done. So to get same amount internal energy at constant pressure, we would require larger amount of heat to be supplied. Hence, Cp is greater than Cv. Krishna, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
1 minute, sir. Done, sir.
Now we have to derive this particular relation mathematically. So we'll say at constant volume, dV equals to 0. So work done equals to 0. So dq equals to du is equals to n times cv dt. Let's say this is the equation first. Now at constant pressure, dq equals to du plus dw. dq is n cp dt, dv as n cv dt, and work done is pdv. Now we have to somehow change this pdv in terms of temperature. So how to solve it? Let's say using ideal gas equation, PV is equals to nRT. Since in this part we have constant pressure, so just divide this entire term with respect to, or differentiate this entire term with respect to temperature. So differentiating with respect to temperature, P is constant, keep it outside. Volume, on differentiating with respect to temperature, it will be dV over dt equals to nR being constant, and differentiation of temperature will be just 1. So from this part, pdV equals to nR times dt. Now put the value of pdV as nRT in this expression, you get so ncp dt equals to ncv dt plus pdv is nr dt. Now take out n dt as common from both sides. So you're left with cp equals to cv plus r, or cp minus cv is equals to r. This is also called Mears relation. Nabila, is it clear?
Yes, sir.
Okay.
Done, sir.
Done, sir.
Done, sir.
Gautam, any doubt?
No, sir.
Okay. So this is all about isochoric or isometric process. There will be some theoretical question related to this part. Why tires of vehicle on long drive get burst? Any idea?
So due to friction, the heat is evolved. Then that heat is
So pressure
to
will
increase.
increase due to increasing temperature.
Good. You'll say on traveling on road, there will be friction in between tires and road, due to which there will be production of heat, which tends to increase the temperature. And since volume of the tire is constant, so at constant volume, pressure and temperature directly proportional to each other. So increasing temperature leads to increase in pressure, and when it exceeds the strength of that tire, it gets burst. So you can say on traveling, temperature inside temperature of tire increases due to friction offered between road and tire, and at constant volume, pressure is directly proportional to temperature. Hence, pressure increases which results in bursting of tire. So to overcome this heating, for long drive, we often use nitrogen gas. Okay. Just write it down.
Done, sir.
Sabila, done?
Yes, sir.
This is entire part of this isochoric process. Next is isothermal.
So can you show the long drive one once again? The description.
Just 1 minute.
Okay, sir.
Next is isothermal process, which is also called Boyle's law. The process which is carried out at constant temperature the process which is carried out at constant temperature is called isothermal process, or simply Boyle's law. Now, according to equation of state, PV is equals to nRT, so temperature is constant. So pressure and volume will be inversely proportional to one another, or P1 V1 must equals to P2 V2. So this will be equation of state. Now, if I have to find the value of x, PV to the power x is equals to constant. So in this part, pressure and volume is equals to, pressure into volume equals to nRT, and T is constant. So product of pressure and volume will be constant. So this entire term, pressure into volume, should be constant. So the value of x to be 1. So using this, molar specific heat at constant temperature Ct equals to R by gamma minus 1 minus R by x minus 1. So if you put the value of x to be 1, so 1 minus 1, 0, and any number divided by 0 will be infinite. So it will be infinity in this case. It means it will require infinite amount of heat to change the temperature of this particular system, or simply say it will be impossible since temperature is constant. Is it clear, Gautam?
Yes, sir. Got it.
Now related to this, we have to plot indicator diagram. First, between pressure and volume, pressure versus temperature, volume versus temperature. Since pressure and volume is inversely proportional to one another, so graph in between them will be rectangular hyperbola like this. From this point to this point, it means On increasing volume, pressure decreases, and on decreasing volume, pressure increases. So it will be inversely proportional to one another. There will be another term. Suppose we have another curve for the same part like this. Let's say this is at some temperature T1 and this is at some temperature T2. So you will be asked which of these two temperature is greater. Krishna, any idea? How to define which of the two temperature is greater, T1 or T2? Good, Yusra. Let me define you. Just draw a horizontal line. Just draw a straight line like this, touching this point at this point and this graph at this point. So if you plot vertical and horizontal related to those different curves, at this point it will be this and this, and at this point it will be this and this. So it will be let's say this is T1 and this is T2 for simplicity. So it will be V1 and P1 and it will be V2 and P2. So according to the equation, PV is equals to nRT. So just multiply P and V. It will give you the value of temperature. So which product will be larger, P1 V1 or P2 V2?
T2.
E2, E2.
T2.
Good. So if the curve goes away from this origin, it will have larger temperature. So you will say T2 will be greater as compared to T1. Nabila, is it clear?
Yes, sir.
Next, for pressure versus temperature, since temperature is constant, so it will be a straight line parallel to opposite coordinate. And since in this part, volume is expanding, so pressure must be decreasing. So curve will be along this way. In third part, for volume versus temperature is constant and volume is increasing, so curve will be along this direction. Yusra, any doubt?
No, sir.
Okay, just write it down.
So why the arrow is pointing down and up?
Okay. We are taking situation of expansion, okay? So on expansion, volume increase or decrease?
Increase.
And since pressure is inversely proportional to volume, so on increasing volume, pressure will decrease. That's why pressure is decreasing in this case and volume is increasing in this case. Both are at constant temperature.
Okay, sir. So we have to draw separately for expansion and contraction.
Yeah. I'm just drawing only expansion part for this entire process. If you reverse the direction of arrow for each part, you will get contraction curve.
That's it.
Nabila, done?
Yes, sir.
Okay. Now, for this part, we have to calculate slope of PV curve. So first is slope of PV graph. Since equation of state for this is pressure into volume is equals to constant. So differentiating both sides, with respect to volume. First, we have product of two different variables. So using product rule, differentiation of first quantity multiplied by second plus differentiation of second quantity multiplied by first equals to differentiation of any constant term, it will be 0. So dV by dV will be just 1, or differentiation of volume will be 1. Move this p to right side. So dP by dV will be equals to minus of p, and this volume on moving to other side will become P by V, like this. Now related to this part, may define bulk modulus. So beta equals to minus of dP by dV multiplied by volume. dP by dV we have minus P by V, so minus minus cancel out. P by V multiplied by V, so V and V cancel out, so it will be just P. It means bulk modulus related to this isothermal process will be equals to pressure of that particular system. Gautam, any doubt?
No, sir.
Just write it down.
So, but why is it minus dP by dV?
Graph is going downward, so inclination will be negative. Since it is rectangular hyperbola like this. So if you draw tangent at any instant to this particular curve, let's say this point, draw a horizontal line to define slope, it will be along downward direction. That's why slope is negative.
Okay, sir.
Done, sir.
Now, next part related to this process will be work done. So how to calculate work done in this process? Work done is simply equals to P times dV integration. Since in this part, pressure and volume both are interdependent in one another, so we have to somehow change one of the variable in terms of some other variable. So for that, let me define using PV is equals to nRT. We may write pressure equals to nRT divided by volume. Now put this value in this expression, you will get just 1 minute. Okay. So put the value of pressure as nRT divided by V. In this, N number of moles are universal gas constant and T is temperature. These three terms is constant, so keep it outside. So left with dV by dV in terms of single variable. So it may have initial volume to some final volume. Yusra, dV over V on integrating will give you, or how to integrate dvx over x. Minashi, integration of 1 over x will be Raza. What will be the integration of dx over x? Is it like x to the power -1 and then +1 whole divided by -1 power +1 or something else? It will give you x to the power 0 divided by 0. So it can't be possible. So
Sir, it
dx
is
over
ln.
x. Good. nRT 1 over x on integration, it will be ln x upper limit, lower limit. Now ln nRT ln upper limit minus ln lower limit. Using property of log m minus log n will be equals to log m by n. So we may write nRT ln V final by V initial is equals to work done. Nabila, is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
You may write this expression in terms of pressure as nRT ln using Pi Vi equals to Pf Vf. So it will be Pi divided by Pf equals to Vf divided by Vi. So just replace Pf and Vi related to this term. You'll get Pi divided by Pf. And this quantity nRT will also equals to product of pressure and volume at any instant related to that curve. Minashi, is it clear?
Yes, sir.
Just write it down. I'm giving you a question.
Sir,
Yes.
but isn't NRT itself the work?
Yes, Gautam?
No, no, sir. I was asking if NRT itself is the work done, right?
Yeah, you may say, but you get multiplied with ln to compensate the required part related to this process. Okay.
Okay. Sir.
Related to this process, try to find these two terms. For first part, just use equation of state P1 V1 equals to P2 V2. Put the value of P1 V1 and V2, you'll get P2. And then for work done, use the above expression and try to find. Good, Raza. Let me give you another value. ln2 equals to 0.7. Good, Minashi. P1 is 2 atm, so you may write 2 into 10 raised power 5. V1 is 20 centimeter, 20 into 10 raised power minus 6. P2 we have to calculate. B2 is 40 into 10 to the power minus 6. So P2 will be 2 into 20 into 10 to the power minus 1 divided by 40 into 10 to the power minus 6. So this part cancel out. So you're left with 1 into 10 to the power 5. Good, Nabila. Pascal. Now, for work done, it will be nRT ln V final by V initial, or you may write nRT as PI VI ln V final by V initial and simplify it. Khalid, just wait for 2 minutes. So if you put PI VI for point A, PI is 2 atm, that is 2 into 10 to the power 5. VI is 20 into 10 to the power minus 6. ln V final 40, V initial 20. So it will be 2 into 20, 40, 10 to the power minus 1. So it will be just 4 ln 40 by 20, 2. The value of ln2 is 0.7. So it will be 4 into 0.7. That is 2.8 joules. Gautam, is it clear?
Sir, why is it P initial and V initial?
You may write P final, V final. You have to product, or you have to take product of P and V at any instant, since
Okay.
PV is equals to nRT.
Good.
Krishna, any doubt?
No, sir.
You all are done?
Yes, sir.
Yes, sir.
Okay, that's it for today. We'll continue in next class after it. Okay,
Thank you, sir.
thank you.
Thank you, sir.
Thank you so much.
Thank you.